Have you ever wondered why the tiny particles in our universe don't always follow the rules we expect? In the elegant dance of the cosmos, where celestial bodies abide by the laws of classical physics, the subatomic particles play by a different set of rules entirely. This is the realm of quantum mechanics, a branch of physics that describes the bizarre behaviors of particles at the smallest scales. Imagine placing a particle in a box. By all classical accounts, it should remain there, yet in the quantum world, it might just pop outside when next observed. It's a world where a particle can exist in multiple places simultaneously, and where certainty is traded for probabilities. The Heisenberg uncertainty principle further mystifies this landscape. The more precisely one determines a particle's position, the less one knows about its momentum, and vice versa. This principle shakes the very foundation of what we know about measuring and observing the universe. This unexpected behavior leads us to ask, do we live in a quantum world? Imagine putting a particle in a box. In the classical world, it stays there. But what happens in the quantum realm? In classical physics, our understanding of the universe is quite straightforward. Objects, whether they are apples or atoms, have specific positions, velocities, and paths. If you know the current state of a system, you can predict its future behavior. This predictability is comforting, like knowing a train will arrive on schedule. Enter quantum mechanics, and the picture changes dramatically. Here, particles such as electrons, photons, or even atoms don't have definite positions or velocities until they are measured. Instead, they exist in a state of probability, spread out over space like waves. This is not just a theoretical abstraction, it's a fundamental aspect of nature that has been confirmed in countless experiments. One of the most intriguing concepts in quantum mechanics is wave-particle duality. This principle tells us that quantum entities can exhibit both particle-like and wave-like properties. For example, light can be seen as both a wave, it can interfere and diffract, and a particle, it can be counted in discrete packets called photons. Similarly, electrons, which are particles, can behave like waves, spreading out and creating interference patterns. This dual nature leads to some bizarre phenomena, such as the famous double-slit experiment. When electrons are fired through two slits onto a screen, they create an interference pattern typical of waves, not particles. But if you try to observe which slit an electron passes through, the interference pattern disappears, and they behave like particles. This shows that the act of measurement affects the system, a concept known as the observer effect. Moreover, quantum mechanics introduces the uncertainty principle, which states that certain pairs of properties, like position and momentum, cannot both be precisely measured at the same time. The more precisely one is known, the less precisely the other can be determined. Thus, the quantum world challenges our everyday understanding and classical intuition. Enter Niels Bohr, the physicist who began to label the quantum world. In the bustling scientific landscape of the early 20th century, Bohr emerged as a pivotal figure. He was not merely a bystander, but a trailblazer who began to decipher the enigmatic behavior of atoms, those tiny constituents of matter. At the time, the atom was understood to be a miniaturized solar system, with electrons orbiting a dense, positively charged nucleus. This model, however, left many questions unanswered. How did electrons move around the nucleus? Why did atoms emit or absorb energy in only specific quantities? Bohr addressed these mysteries with a revolutionary idea: quantized orbits. According to Bohr, electrons in an atom could only occupy certain allowed orbits. Each orbit corresponded to a specific energy level. Electrons could jump from one orbit to another. However, these transitions would result in the absorption or emission of energy in discrete packets called quanta. This was a radical departure from the classical view, where energy was considered to be continuous. Bohr's atomic model was a blend of ingenuity and practicality. It proposed that as long as electrons moved in these quantized orbits, the atom would remain stable. This was a significant leap in understanding atomic stability and electron behavior. Despite its simplicity, Bohr's model provided a robust framework that explained many experimental results of the time. Yet it was clear that Bohr's model was an approximation. It worked well for hydrogen, the simplest atom, but struggled with more complex elements. This limitation, however, did not overshadow its contributions. Bohr's approach was instrumental in moving the scientific community towards a more complete and sophisticated quantum theory. As science progressed, Bohr's model evolved. It laid the groundwork for the development of quantum mechanics, a theory that has since permeated every corner of physics and beyond, reshaping our understanding of the universe. Bohr's groundwork laid the foundation for a deeper understanding of the atomic structure. Bohr didn't just stop with an atom model. He introduced a transformative idea, the correspondence principle. But what exactly is this principle, and why does it matter? Let's delve into these intriguing questions. The correspondence principle is fundamentally about making sense of how quantum mechanics transitions into classical physics, the physics of our everyday experiences under certain conditions. It states that the behavior of systems described by quantum mechanics replicates classical physics when the quantum numbers involved are very large. Imagine you're observing an electron in an atom. At the quantum level, it exhibits behavior that defies classical intuition, existing perhaps in multiple states at once. However, as these quantum numbers grow, reflecting conditions such as higher energy levels or larger angular momenta, the electron's behavior starts mirroring classical predictions. It begins to trace a path more akin to a planet orbiting the Sun, which is a classical motion we can easily comprehend. This principle does not just apply to theoretical musings, it has practical implications. For instance, in the realm of large objects or actions like a basketball arcing through the air, quantum effects become negligible. The basketball doesn't blur into a probability cloud of potential positions. Instead, it follows a predictable parabolic trajectory. The correspondence principle assures us that the quantum laws governing the microscopic particles composing the basketball give way to the classical laws of motion we observe. In essence, Bohr's principle acts as a bridge, a conceptual and mathematical bridge between the enigmatic quantum world and the macroscopic world we navigate daily. It reassures us that our classical equations are not just approximations, but are deeply connected to the quantum rules. They emerge from these rules under the right conditions. This principle is crucial, asserting that quantum and classical physics aren't adversaries, but are interconnected at fundamental levels. Through the correspondence principle, we see that the universe is a tapestry woven from threads of quantum and classical laws, each indispensable in understanding the full picture. How then do the strange rules of the quantum world give way to the predictable laws of the macroscopic world? Imagine a bustling city seen from afar. It appears as a single entity, yet it's composed of countless individual stories and interactions. Similarly, the macroscopic world we experience every day, everything from the flow of water to the solidity of a desk, is the cumulative effect of countless quantum interactions. At the heart of this complexity is the concept of emergence, the idea that whole systems can exhibit properties and behaviors that their parts do not possess on their own. For instance, take temperature. Individually, atoms do not have temperature. Temperature is a collective property that emerges from the energy of particles moving within a substance. This phenomenon of emergent properties is where quantum mechanics begins to blend with classical physics. Quantum mechanics governs the bizarre and probabilistic behaviors of particles at incredibly small scales. When scaled up to the billions of particles, these quantum effects average out, resulting in the deterministic laws that we observe in classical physics, such as Newton's laws of motion. Yet the transition from quantum to classical is anything but seamless. Researchers are still trying to pinpoint exactly how and why this transition occurs. One leading theory is decoherence, which suggests that quantum systems lose their quantum properties as they interact with their environment, effectively becoming entangled with countless other particles until their quantumness simply dissipates. Moreover, cutting-edge experiments continue to push the boundaries of our understanding. Scientists are now able to observe quantum effects at increasingly larger scales, challenging the traditional view of where quantum rules end and classical rules begin. The journey to fully understand this connection is ongoing, filled with both mystery and opportunity. As we delve deeper, we uncover more questions than answers, but each discovery adds a piece to the puzzle of our universe, linking the tiny quantum world with the vast expanse of the macroscopic. Our exploration reveals a universe far more intricate and mysterious than we could have imagined. As we journeyed through the realms of classical and quantum mechanics, we uncovered how these two frameworks paint vastly different pictures of our world. Classical physics, with its predictable certainty, stands in stark contrast to the probabilistic nature of quantum mechanics, where particles can exist in multiple states simultaneously until observed. Niels Bohr, a pioneering figure in this quantum narrative, introduced concepts that still resonate within the corridors of modern physics. His early models of the atom and the bold correspondence principle bridged the seemingly vast chasm between the quantum and classical worlds. This principle suggests that quantum behaviors smooth out to align with classical laws under certain conditions, a profound insight that guides much of today's quantum research. As we continue to unveil the quantum landscape, we edge closer to understanding the very fabric of our reality. The journey is far from over, and each discovery is a step toward unraveling the universe's deepest mysteries.